and you see that's instant. And yeah, let's check the results. So we would expect 190 something, and yeah, 193. Hey guys, welcome to this video. Today we're gonna take a look at 2D meshing capabilities in Inspire. So let's get into it. This will be based on a tutorial or a course material you can get also for free. I will put a link in the description where you can get the full course material. And this is module 2, where the goal is to just learn about the 2D meshing capabilities and how meshing affects also performance or the output here on an example with a plate. And yeah, let's just go through here. All right, so we have this model here. I have loaded the model here into Inspire, and you see the geometric dimensions here. So we have 40 millimeters. This is the diameter of the hole. We have 120 millimeters width and 500 millimeters length of the plate. And the thickness of the plate is 3 millimeters. And this is loaded with 20 kilonewtons at one side, so pulling in one side, and the other side is fixed, right? So, well, first of all, what is here also shown is that you can get the stress concentration factor, which is how much more stress you would have here because of the geometric imperfection of which is this hole, compared to a nominal stress you would guess at a full cross section. We will see that in a minute, but you can get this KT factor, which is the stress concentration factor, on here. So let's check that out. So if I just open this thing here, you can search for maybe a hole, and then you have a central circular hole and a finite plate. This is exactly what we need. Now the diameter was 40. No, sorry, that's the width. That was 120. The hole diameter was 40. The blade thickness is 3, and the tension force would be, well, it doesn't matter too much here, but yeah, let's put it in. No in-plane bending moment and no transverse bending moment. So let's calculate it here. And you will see indeed that you have the stress concentration factor KT of 2.3. Yeah, basically that's dependent on the ratio of the small d to the capital letter D. Yeah, but anyhow, you see now that we have the stress concentration factor, and what does this really mean? So basically, if we would just assume here a cross section, then the cross section area would be 120 times 3. But now we have the hole here, so we have to deduct 40 millimeters from the 120. So you would be left at 80 millimeters of width, which has structure, and 80 times 3 would be 240. So 240 square millimeters on a cross section here. And now if you have that and you have your 20K, then let's just do a small calculation here. So we have 20K divided by, now I will just make the full calculation, 120 minus 40. Oh, that was too much. Sorry about that. Let's make it sure. So 120 minus 40, that's 80. Times 3, that's 240. All right. And now we have 20 kilonewtons divided by 240. So that's 83 newton per square millimeters, or MPa, megapascals. That's what you would assume of a normal stress on this cross section. But now you have the KT factor, which is the stress concentration factor, and this will bump this value up by a factor of 2.3, and now you're arriving at that value, and this value is then the stress value you would expect the FE solution to converge to, right? So this is roughly the thing where you should land. And now let's check that. Let's check that with various mesh sizes and see how this goes. I think we can also just look at here the slides before we do it in real time. So we have here now different element sizes, 20 millimeters, 10 millimeters, 4, 3. And just that you can guess what it is, you can see the pictures here. So 20 millimeters is a mesh like this, 10 millimeters, 4, 3, 1. So just from what you see here, 1 seems like a decent mesh, right? Small enough, yeah. But if you see now the stresses which will come out here, so okay, 20 millimeters completely off the charts. We have a maximum stress here of 90 megapascals compared to 190, so we are way off. Then we have the next one with 10 millimeters, that's 116, not too much better. Then 150, then 160, but still. And then at 1 millimeter, we are finally going in the right direction with 186. But you see, the mesh is quite fine at that point. Yeah, also pay attention to this setting in Inspire that you can switch between faster and more accurate. I'm not 100% sure because I didn't check, but I think this is the element formulation which is changed from linear elements to quadratic elements. And yeah, so all right, summarizing here, 20, 10, 4, 3, and 1. You see the relative error. So when you do a meshing, you really have to check whether your mesh has already converged, meaning that if you decrease in size, it does not decrease too much in stress value. And to be honest, here I would not say this is converged yet, because we have now an error of 2.97, 2.97% of an error. To the theoretical value, that would be okay, I think, but just from 3 to 1, it went up from 160 to 186. So yeah, it's a gap. So you could just do one more round, but 1 millimeter is pretty fine already. So well, it's doable, but still. The question is, do you really need those elements here to be that fine? So on this side of things, because there's not much happening here. Basically, you're just interested in here to get a really fine mesh. And that's a thing we also want to check. And here you can see if you choose to have accurate instead of faster, then it will change a little bit, but not too much. All right, yeah, so that's that. Okay, basically, that's just a run-up on what we're gonna do. We will not do all of those things here, but just to show you, or just to go through the process of choosing different mesh sizes. And I wanted to also show you a technique how you could differentiate between different zones in your model, even in Inspire. All right, so let's do this. Let's go in here and see how we could change mesh sizes. And the first thing we need to really check is that we have in the preferences under run options the OptiStruct solver. Because if we have the SimSolid option, there's no mesh. And even worse, if you have the SimSolid solver and want to do something like this, it will not work because no solid part. SimSolid, solid, can only run solid parts. That means parts with volume and not simplified parts where this plate is just modeled as a 2D plane, and therefore SimSolid cannot do that. But we will do SimSolid run after we have covered the OptiStruct run and see how this goes, because SimSolid has a pretty fast way of getting accurate results. And so that's another highlight I want to make in this video. All right. Okay, so we have to check that we have in the preferences under Inspire run options, we should have OptiStruct as a solver. And all right, hit OK. And if we now press on Analyze, you see it has a mesh size here, and also it says Run OptiStruct Analysis at the top. So that's fine, that's all right. And now we can choose the element size. And just that we have something which runs decently fast, we will go with 10 millimeters and just check faster, because it doesn't change too much here. So let's go like this and run it. So basically what this was setting, that's setting a global mesh size. It's not part specific, but it's rather a default mesh size, you could say. If you have multiple parts in your model and want to, for example, have this part meshed differently than your global setting, then you can go into the property editor and see there's a mesh sub point here, where you can press here on override, and then you can set two values. The min element size, that's the minimum element size which is which should appear in this part. And the other one is the average element size. And those two things, they are constrained together. You cannot set them equal because I think there should be a ratio, I think 1 to 5 or so. The solver will complain if you set them wrong, but just as a rule of thumb, I would say take your average size. Let's say that's, for example, 3 millimeters. And then your millimeter element size, for example, of so 0.2 times 3, for example. So let's go with 0.5, for example. Yeah, so this should work. We can check that also and in a bit, but it will take a little bit to run it. So, okay, now this one has finished. This has 10 millimeters, and you can see now the von Mises stress is around at 116. Is that the same we had here? Let's check. 10 millimeters were 116.4. Yeah, we have a little bit different results here, but that's all right. So 116 still way off, 40% error. That's not too good. Okay, but now just to see the mesh. If you don't see the mesh, that's done with the button here. This button chooses different styles, and yeah, so you can see the mesh. By the way, that's also a little bit of a pity, but the meshing occurs when you analyze the structure. It does not occur in the pre-processing. So you have to run it in order to see the mesh, right? Okay, now let's choose another run, and then let's just give a silly element size here and press run. Now, although I gave a rather big number here at the element size, because I set in the only part which is available here, the override button, it will respect this element size. And that you don't have to wait all the time until it's finished. I will just hit the pause here and we'll see you in a minute. And we're back. So we have now a different mesh. And let's just see here. So I think I specified 3 to be the average element size. If you want to measure, just take here the measure tool. Let's see how the thing is. So 3 millimeters. So it did not really decrease in size. Okay, now we are at 160, which, yeah, pretty much corresponds to the result we are expecting to get. Now, you see, you have a hotspot here, as expected, right? And this hotspot needs a finer mesh. So that's clear. But you don't necessarily need the mesh this fine in this region. So you could do a little bit of a trick. You could separate this part into 2 parts and then choose different meshes for different parts. Let's just do that and see how this goes. And also another thing I want to say, be careful with what you're setting here, because that was also a thing which I saw here in the tutorial. If you set it like this, so 20 millimeters minimum and average 107, that was a funny observation. So let's say 20 and here 120, for example. Let's just run it again. This will be pretty fast, and that will be pretty interesting, because now the mesh size, just that you see from the distance. So from here to here, it was 120. If we define an average of 107 or 120 in this matter, the element size would be this big, right? There's no way we could resolute this hole here. And that's pretty interesting what the solver here now does. It will effectively ignore the hole here and just mesh as if there was no hole. And that's a thing which you have to be careful about. If you have small features and define a mesh size with the override, which is larger than the mesh size which is needed to respect all the geometric features you have in your model, then you can end up with something like this. And you can see here now you have 4 elements, but this is no way that's correct, right? So this is not your geometry, that's not the thing what you want, and yeah, so just be careful about that. Good. Now I wanted to show you how to do a partition on this model, and this starts with creating a sketch on the part you want to partition, And then let's just add a circle around your hole here. So let's say this would be 40. Let's go with a buffer size of 20 millimeters. So roughly 60 millimeters. Okay, now we have this thing, and in order to that this is respected, we have to trim now the part here, which is done in the geometric ribbon and then on the trim split. And now you have to be a little bit careful. So you have targets and tools. The target is the thing we want to split with this thing. So this would be the whole surface. And the tool will be the line. Be careful that you don't select the surface. Then project along z-axis is correct. That would be normal to the plane. Yeah, that would be the z-axis. And then you have to also say what you would want to keep. And here you can also see it's light gray. That would be deleted if you have it like this. But if you choose both, then you have both in gray and through all. That's also good. And I don't think we need to extend or the keep resource as surface. So let's check if this works. And indeed, we have now two parts which are connected. So sketch can be ignored, but you see now you have this part here and the part here, right? Now you can do the following. You can just uncheck the override button here and just go to this surface and check the override button here. And let's go with something really small. So 0.2 and 1.0. And maybe let's go with the override on the other one too, just to make things a little bit. So the minimum mesh size should be 1, because it has to have this intersection here with 1, but the average element size can be 15 or so. It's a little bit dependent on, the mesh will not look that good, to be honest, because we have to really make a shift between a coarse mesh to a finer mesh, and this will have its trade-off here. But as we just really want to take a look at here, I would say it's all right to do this. Okay, well, let's go with it and run the analysis again. Again, does not really matter what we put in here because we have put override to both of our parts, and thus we specified exactly how the mesh should look like. Okay, again, I will hit the pause button and be right back. And we're back. So let's see. All right, now we're getting in the right direction, right? So 175 is pretty close to the one we would expect. And you see the element count is not too high. I know the element here. Those elements look like not so good, right? But can be tolerated if you just are interested in what the hotspot looks like, because stiffness wise those elements work just more or less fine, but you cannot really do a stress analysis on here. All right, so this is the technique I could recommend to you if you won't have a problem with runtimes. But now I promise to you that we would also look into the SimSolid side of things, because there you don't have anything to do with meshing, because SimSolid, the solver there, is a meshless solver. So let's check it. Let's check accuracy and also time here. For this to do, I will just go with a fresh new model and just drag the geometry back in. Or more or less the model. It's small that it's more than the geometry. The boundary conditions are there too, but let's delete those boundary conditions, as we have to do a operation first. We have to make a solid out of it. So we press the letter P on the keyboard to go into the push-pull, select the surface, drag it out, and specify 3 millimeters to extend this plate to be a solid part. Now, I hope that's all right. So direction was correct. And now let's add the boundary conditions again. Go to structure, to the constraints. Let's just select this surface to be held in place. You see now you don't have the rotational degrees of freedom anymore because you don't need them in 3D. And let's add the force on the other side, this time not on the edge, but the whole surface, 20 kilonewtons. And let's change it in direction. that it is pulling. Correct. And now let's run it. First thing, File, Preferences, Run Options, change that to SimSolid. And now on Analyze, just hit whatever. Here we really can spend a few seconds more to go for stress. And let's run it. And you see that's instant. And yeah, let's check the results. So we would expect 190 something. And yeah, 193. I mean, the kind of how it's displayed is not too much. It's not too good, to be honest. It looks like a coarse mesh, but the value is perfectly right. That's because it's a meshless solver, and therefore does not need this kind of refinement and check for mesh conversions. All right. Yeah, so basically that's the content of today's video. So we covered OptiStruct, the different kinds of how you set the mesh sizes in Inspire per part or in general, the different element formulations, and also compared the SimSolid solver to it. Hope you had a great time. If you have any questions, leave a comment below, and I hope to see you back in the next time. Cheers, guys.